In this video, I'll be talking about binding energy and its relation to fission and fusion. This is part of topic 7, which is in the SL and HL part of the IB Physics Syllabus. Please take a moment and read the success criteria for this video. So let's look at this graph a little closer. I introduced it in our previous video. What we have is the binding energy per nucleon, and this shape is really important. First of all, take a note that we have a peak here at iron 53, and we also have this small little peak here at helium 4. Now, that actually should say He, not Hc. We're going to talk about how when we had the binding energy, and that was the energy released when all of the constituent parts of the nucleus came together. When the protons and neutrons, which were separate, came together, they released energy. We have a smaller mass of the nucleus compared to when they were separate. That mass didn't just disappear, it turned into binding energy. Now, the amount of energy released per nucleus is very small, but I do want to point out that just like in chemistry, here in physics, we also need to talk about a mole. And 1 mole is 6.02 times 10 to the 23 atoms. That's Avogadro's number. And what we have here is these values of 235 uranium end up saying that if we had 1 mole of uranium, it would weigh approximately 235 grams. That's a lot of atoms, which is why you'll see we have a staggering amount of energy that can be released from just a small amount of fuel. So, what can we actually read from this graph? Its shape, as I said, is very important. First of all, if we had just binding energy, larger nuclei are always going to have more energy than smaller nuclei, just because there's more of them. But if we look at this binding energy per nucleon, you're going to see that those larger nuclei actually have less binding energy per nucleon than something like iron 56. Remember, I said that is our peak there. So all of these past there have a reducing amount of binding energy. Likewise, because it's the peak on the left side, all of these have a smaller binding energy per nucleon. This is really key because the higher the binding energy per nucleon, the more stable the nucleus is. We're going to talk about how if I have larger nuclei, we're more likely to get fission, that is breaking apart of the nucleus into smaller pieces in order to have a greater binding energy per nucleon. Likewise, if we can get them to come together, which is fusion, we're going to get a more stable nucleus as well. Okay, so let's take a look at fission first. Fission, just like in any other use of the word, means to break apart into smaller pieces. We talk about fission in terms of yeast dividing, and here we're going to be talking about nuclear fission, obviously, a nucleus breaking into smaller pieces. Now notice that if I have something like uranium-235 up here at the top, if I can get it to break down into smaller pieces that occur in this area here, they will have more binding energy per nucleon, which means they would be more stable. I have here a reaction, one that you're going to see in topic 8 later on when you talk about nuclear reactors. I have a neutron combining with a nucleus of uranium-235, and together they're going to make uranium-236. Now this nucleus happens to be unstable and it can break down via fission. Now in this case I've got it breaking down into barium and krypton, which are most likely, but it's not actually always those two particular atoms. What will need to happen is that whatever it breaks into are going to have a higher binding energy per nucleon. Now in this particular case, we also get 3 neutrons. Notice that those 3 neutrons could go back and hit another uranium-235, and this could also then cause another reaction. So if you think about it, one reaction made 3 neutrons. They could go on to make 9, 27, 81, and basically kaboom. That's the difference between your nuclear reactor and your hydrogen bomb. You'll learn more about that in topic 8, about how you can then just make sure one neutron will then make one more neutron to then continue the reaction. If not, we call this a chain reaction. Hopefully it's obvious by now, as I've been talking about this, energy is definitely released in this process. So let's talk about fusion then. So if fission is a large nucleus breaking apart, fusion is the opposite. We have small nuclei coming together to make a bigger one. Now that won't occur over here because if these combine to create a larger one, it has a smaller binding energy per nucleon. We're going to get fission, and it's going to have to be on the left side of iron 56. So I've got an example here that could possibly happen in the sun. I have H with a 2, that's deuterium. So that's hydrogen that has a nucleon number of 2. That would be 1 proton because it's hydrogen and 1 neutron. And it's combining with tritium because there's a 3 for the nucleon number. That again is 1 proton, but 2 neutrons to make hydrogen. These two isotopes are so common that we actually give them their own name. Now, if these two combined and made helium, remember 2 protons, 2 neutrons, and 1 other neutron, this reaction would actually give off energy, which is why fusion is then what we say is powering the sun. This takes a lot of energy to happen, and if you've ever heard about cold fusion, that's the idea that it's happening basically at room temperature or something other than the sun. The sun has such a high temperature and pressure in the center that we get these that we can get these nuclei close together to create one nucleus. So what about fusion then? Now we're going to have much smaller nuclei combining together in order to make a single nucleus. Now in this case, you see I have H2 and 3 hydrogen. Now they are deuterium. So deuterium right here would be, because it has a nucleon number of 2, that's 1 proton because it is hydrogen, and 1 neutron, giving it a total of 2 nucleon number. This is deuterium. Here we call this tritium. There's 3 as a nucleon number. That's 1 proton because it's hydrogen, and it will have 2 neutrons. Now, if I get them to combine together, I can get helium, which will be 2 protons. Remember, the number of protons determine the element, and it releases off 1 neutron. This would be an example of fusion. This happens typically in the center of the sun. Obviously releases a lot of energy. It's the fuel for the sun. Now, if you think about it, we've got 2 positive nuclei coming together. It takes a lot of energy to do that. So the high temperature and pressure at the center of the sun makes this possible. If you've ever heard of cold fusion, that's the idea that we could somehow make it at more room temperature levels, or something we can reproduce in the laboratory compared to the center of the sun. Again, this gives off energy, which is why people are trying to recreate cold fusion as a source of energy. More to come in topic 8. So let's take a look at a couple of different examples. So it tells me that this is a possible fission reaction. We've got uranium-236 breaking into tellurium and zirconium. Remember I said it's not always krypton and barium. Now it's telling us that we've got the binding energies, and it's looking for the relationship of the binding energies of the products and the reactants. Now one of the things, it's fission, it's going to then release energy. Another thing I want you to recall is that the products are going to be more stable with binding energy per nucleon than the original daughter nucleus. That means they're going to have a greater binding energy per nucleon than the initial nucleus. So what is the answer? C. The binding energies of tellurium and zirconium are going to be bigger than uranium. Okay, on to another example. The process represented by 3,2 helium, 3,2 helium coming together to make 4,2 helium and 2 hydrogen would be described as. Now, in a way, I think this is easiest answered by talking about what it can't be. Well, it's not an alpha decay. Yes, it's true that we could say the 4,2 helium might be an alpha particle, but an alpha decay would be coming from one single nucleus releasing the alpha decay. So it is not A. Now, nuclear fission, that is one large nucleus breaking down into smaller pieces. Definitely not here. We have things being combined, not fission. Let me drop down to the last one. Scattering of helium by helium. Now, scattering, we also talk about electron scattering, photon scattering. Scattering just means a change in direction of the particles. There's actually no combination of them or other than changing direction or that kind of interference. So this is not scattering. It does leave fusion. So let's think about it. Do I have two smaller atoms combining together, and I should say two smaller nuclei combining together to make a larger nuclei? Yes. So this would best be described by fusion. What about this one? The binding energy per nucleon of the nucleus 7,3 lithium is approximately 5 mega electron volts. What is going to be the total energy required to separate the nuclei? Now, if you remember the definition of binding energy was either the energy released when we have our constituents of the nucleus put together, or the amount of energy needed to separate the nucleus into its individual pieces. So in this case, we're going to use the second definition. I have 7 pieces I have to separate. So if each one of them has a binding energy per nucleon of 5 mega electron volts, I will need to have C, 35 mega electron volts. Now, this would be a really good time just to remind you, yes, I just had 3 questions where the answer is C every single time. Please don't let that influence your decision when you're making your answers on an exam. You cannot assume that they will never repeat a value, and there could be 3 or 4 in a row. And there's a big danger of saying, oh no, I've got 4 in a row, the next one cannot be C. Because how do you know every one of those 3 were already correct? Okay, so treat each question individually. Okay, so in this question, I have a diagram helping us out here. It's telling us about the first stage of fusion between 2 protons to make a deuterium nucleus. Take a look at the arrows and make sure you're familiar with what the products are and what the reactants are. So the first part of the question says, complete the nuclear equation to represent the fusion of the 2 protons to form a deuterium nucleus. So it has here that the 2 protons are coming together, and if you look at the arrow, it says we're going to give off the deuterium nucleus and a positron and a neutrino. So there we go. We have the deuterium. Remember, I said it's so important. It's a specific isotope of hydrogen. We call it by name. There's my positron. You also could have written E with a plus sign and a neutrino. I could also include the fact that it's an electron neutrino because it was created at the same time as the positron. So next, calculate the energy in joules emitted in this first stage. Well, the first thing we're going to need to do is talk about how we're going to get the mass defect. Remember the change in mass when I take the constituent parts and put them together. We also have this unit here called mega electron volts per c squared. Now, per c squared means that this is actually a mass, not an energy. If you think about Einstein's equation, E equals mc squared, basically what we have here is mass is E per c squared. So mega electron volts is a unit of energy. So since I have it divided by c squared, I then have a unit of mass. So if I first go and calculate the change in mass, I will be on my way to be able to calculate, using our equation E equals mc squared, the change in energy. Okay, so you can see here I've calculated the mass defect, or sometimes places call it the mass deficit. I've started off with having the mass of the proton times 2, because I have 2 of them. I've subtracted off the mass of the deuterium and the mass of the positron. If you remember, the neutrino doesn't have a mass. When I do that, I calculate the difference in mass as being 0.41 mega electron volts per c squared. So if I want to turn that mass into an energy using our equation energy equals mc squared, then really all I'm doing is getting rid of this c to the minus 2, so that my energy is going to be 0.41 mega electron volts. Now, notice the question says I have to answer this in joules. So if I only got to there, I would miss the last mark. So remember, 1 electron volt is the amount of energy needed to move an electron through 1 volt. So that means if we use the idea of volt is joules per coulomb, if I want the energy required for that, which is the electron volt, I'm going to take 1 volt and multiply it by the charge of an electron. That gives us the relationship of 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So if I'm now going to change this energy into joules, I'm going to take our 0.41 times 10 to the 6, remember, because it's mega electron volts. If I multiply that by 1.6 times 10 to the minus 19, I will end up with 6.56 times 10 to the minus 14 joules. Again, that sounds like a really small value, but when you consider that's for one nucleus and the number of nuclei we will have, remember Avogadro's number, this is a large amount of energy. Okay, so here's another chart here, and let's do some other sample calculations. First of all, calculate the binding energy in mega electron volts of a tritium, which is 3,1 hydrogen nucleus. So that would be 2 neutrons and 1 proton. I'm going to have to calculate the amount of mass of the constituents, subtract the mass of the actual nucleus, and then make sure we've got the right units. Okay, so you can see my working there. When I've done this, then I have to double check the units that were in my chart. This says atomic mass units, but what I need is an answer in mega electron volts. If you recall, we can find this relationship in our data booklet. You'll see that 1 atomic mass unit is equal to 931.5 mega electron volts per c squared. I just want to point out, when these values are in our data booklet, we need to use those ones. I know some places and some different exam boards will round that to 930, but since it's given to us, we need to use all of these significant figures. If I then change my atomic mass unit into mega electron volts, I will get the value of 8.49 mega electron volts. Make sure you can check that out for yourself. Now, in the next part, the total mass of the separate nucleons that make up a polonium-210 nucleus is given as 211.70394. Calculate the binding energy per nucleon of polonium. You're going to use the exact same process. So hit pause and test it out. Using the values from the chart, you should find that your change in mass is going to be 1.76672 atomic mass units. But it's asked for the binding energy per nucleon. So make sure you've tried it out. And notice I've changed my answer into mega electron volts per nucleon, the more traditional value. You should receive a value of 7.837. Why did I keep only 4 significant figures? And that's because that's all I have here in my um, conversion between atomic mass units and mega electron volts. So, one more piece. One possible fission reaction is uranium-235 plus a neutron, eventually giving us barium, krypton, and the 3 neutrons. By reference to binding energy, explain without calculation why this reaction is energetically possible. Now, a couple things I want to point out. It says by reference to binding energy. So there might be other possible answers, but you will only get marks if you refer to binding energy. Now, in this case, I actually would suggest that you draw the graph that we keep referring to, the binding energy per nucleon. Don't forget to label the axes. Even though it doesn't ask for a diagram, you can do diagrams to support your answer. But if I just left it like that without any words, I wouldn't actually get any marks. But it's going to help explain my response. So I would suggest you include it. So from the graph, we know that the binding energy per nucleon for both krypton and barium is going to be greater than that of uranium. That means when it breaks apart, we're going to be creating more stable nuclei than we had at the beginning. That's why this fission reaction is going to be energetically possible. So if you take a look at those success criteria again, I hope now after our bit of discussion and examples, you can now say yes to these success criteria.